Hello, everyone. So, welcome to episode two. I hope you got something out of episode one. And just to quickly summarize what I said last time was the main couple of differences between Newton's viewpoint and Einstein's viewpoint. One big difference was the math used. The math in Newton's world was a lot easier to work with, to do experiments with. The math in Einstein's world is very complicated. It is very abstract. It is very, very hard to understand. And you really do need to kind of go on in schooling if you really want to understand it in any deep way. So that was the first kind of big difference. The math is very, very different. The second big difference is the fact that in Einstein's world, you can only go as fast as the speed of light, which means that your velocity, you can only go the speed of light. That is the maximum speed. So to give it some analogy to real life, an Einstein point of view would be, I'm on highway, the 407, and I see it says 100 kilometers an hour as the speed limit. And instead of going 100 kilometers an hour, you decide to go 120 kilometers an hour. That would be a Newtonian world. But in the Einstein world, if it says the speed of light is the speed limit, I'm not allowed to go past that speed limit. I can't just add 10 kilometers and say, now I'm going to go faster than the speed of light. It just doesn't work like that. It is not the same thing. So that was one of the big conceptual differences. So I want to talk about kind of something related. So this was kind of something that Newton knew. Newton, after he created his theory of gravity in the 1660s, 1670s, he was a very, very smart man, genius, and he understood the fact that in terms of gravity, he knew that there was something a bit absurd about the way he describes it mathematically. He understood that there was something wrong, that the way that he had, the math he published and put forward worked very well, but it wasn't correct. It wasn't completely correct. It wasn't the full picture. It wasn't the right way of talking about it, but it worked. And so what did he think was one of these problems? And I have a quote here, and I'm just going to read it a couple times just so you can hear it again. And what this is from 1687, and this is letters from Newton to Richard Bentley. So this was in the 1687, and this was from a person named Michael Faraday. Now, Newton still had the same positions as him, but this is something that was a conversation point around Newton's big theory of gravity he had published at the time. And let me just read what this problem that he found it was. It goes like this. That one body may act upon another at a distance through a vacuum without the mediation of anything else, by and through which their action and force may be conveyed from one to another, is to me so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. Let me repeat it one more time. That one body may act upon another at a distance through a vacuum without the mediation of anything else, by and through which their action and force may be conveyed from one to another, is to me so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. Pretty harsh words, very British, but very, very harsh. So what is this saying? So this is a very famous problem that has been well studied now, which is called action at a distance. And I would recommend looking at the Wikipedia page. There's an entire Wikipedia page devoted to this discussion. But I want to just briefly go through what the problem is here, because it's essentially saying that if you believe in Newton's theory of gravity to the extent that you think it's the end-all be-all, if you have any capability to think, I cannot believe that you could actually believe this. And it wasn't really that what Newton's theory was wrong per se, but it was the interpretation that could come out of it that was incorrect. And let me explain a bit about why they're saying this. So similar to last time, you've heard of this equation called F equals ma. So F equals ma is, this force times mass equals mass times acceleration, that kind of thing. So there's another equation that Newton came up with, and it has to do with the force of gravity between one object here and one object here. So for example, it could be the force of gravity between me and this glass of lemon water. It could be me and this book, the force between us. So what do you need to do to calculate this force? Let me give an example using these two items. So I have my book here and I have my glass of water here. So all I need to do to figure out what is the force of gravity between these two objects, I just need to know how much this one weighs, what is the mass of this object, and how much this one is. What is the mass of this object? Now once I've figured out the mass, I need to set it up in such a way that I can figure out what the distance is between these two objects. So right now it looks about a foot, so about 12 inches in distance. So what I can do now is I just have to take that distance. I have to divide it by 2 because in Newton's world, he works with something called radius. But anyway, you divide it by 2 and then you square it. And what else you need to do is you need to take the mass of this one, the mass of this one, multiply these two together, and then divide it by that radius squared. And then there's some constant that you multiply by, but that's not important. The main idea that you need to take away from this is that you need to know the mass of the two objects and then how far away they are. Once you know those three things, you can figure out the gravity between them. So what's wrong with kind of the thing I described there? So the equation he came up with is mass of object 1 times mass of object 2 divided by essentially the distance of these two objects. So what is wrong with that description? What is wrong with that description is that it assumes essentially that you have a gravitational force to every object in the universe. Because all I'm saying to you is, if you can calculate the distance between us and the star Orion, you have a force of gravity on the star of Orion. If we could figure out the mass of that star and figure out the mass of you, we can pretty much know the distance, and then we can figure out what the force of your gravity on that is. Now the interesting thing is you'll notice that it depends on how far away you are. So let's say you're walking around your house. What this is saying is that as you walk around your house, you exert a different amount of gravity on that star every time you're walking around. Just walk around your room and you've now changed the amount of gravity that you're putting on this star that's millions of light years away. And why does that make no sense at all? It makes no sense because the speed of light is as fast as something can go. So how is it possible that you could be millions of light years away, which essentially means that it would take 1,000 years for light to get from you to that star? That's what that means, a light year. How does it make any sense that could be possible? And it turns out that is what is being criticized in this passage. The fact that it doesn't make any sense that you could essentially instantaneously travel millions and millions and millions and millions of miles away and exert some kind of force on that, and it could exert force on you. That doesn't make any sense. Intuitively speaking, it's in our day-to-day lives, we pick up this glass, I do stuff with it, I move it around, I put some force on it, I can push it on the desk, I can knock it off the desk, I can drop it, I can do many of these things, but there's some kind of way to bring that force to it. It's kind of like this. It's like using the Force in Star Wars. Let's imagine that every kid has tried to use the Force. You tried to do some kind of Jedi move on someone else, and it doesn't work. And why does it not work? Well, there's no way to carry your mind reading ability from where you are to your friend, and there's no means of essentially of producing that effect. There's no mechanism to get you there. There's no vehicle that you have that can bring your mind mind reading abilities into the real world and bring it over to that person, and then you're now in their mind, and then bring it back and then have that information in your head. There's no method by which you can do this. Similarly, there's no method by which you can levitate objects without touching the object. So for example, if I try to use my mind to levitate this glass, it's not going to work. However, if I take my hand, this is my vehicle, and I pick it up, well, now I've done exactly what I thought I wanted to do. And now I have the ability of, picking this glass up. I can toss it. I can do different things with it. But I have a way of exerting some kind of force on this object by doing this. And this is something that's very, very familiar to everyone. This kind of thinking. It's very intuitive to us. What is not intuitive is that a star like Sagittarius or the center of the universe is having a force exerted on by you every time you walk around your house. That doesn't make any sense. That is simply a bit ridiculous to you. Okay, so how does Einstein come in and fix this? Because clearly you're not allowed to go faster than the speed of light. And it obviously doesn't make any sense that gravity essentially just moves in some weird way. It's just everywhere, and it just chooses how much depending on where you are, essentially. So it doesn't really make any sense. So what did Einstein kind of come up with? And I have a little graphic here to show a bit of what I want to mention. So here you can see this book. So this is a general theory of gravity, a relativity book. And I don't know if this is very clear, but essentially you can see this kind of this grid, and then you see there's like some kind of like hole of some kind of thing, and that kind of thing. So to kind of explain Einstein's viewpoint, think about like if you would have gone to the zoo as a kid. When you go to the zoo, there's like that plastic kind of thing where you can like take a coin and then put the coin in, and then the coin kind of zooms around this bowl for 30 seconds or something, and then it eventually falls down, and then it stops. You could think about gravity in Einstein's world as doing something a bit similar. So if you took your bed sheets off, and let's say you had 3 friends over and you want to try and do something fun, what you would do is you would have all of your friends hold on to one of the corners and then pull it, each of you, as tightly as possible. So once you've done this, what you can start doing is you can start taking kind of circular objects and just start throwing them on this bed sheet. Get someone else to throw these on. So if I throw something like a toy soccer ball, this fluffy thing, your expectation is that when I throw it on, you really won't notice it. It's probably going to bounce around, and it's probably not going to cause your bed sheet to kind of deform. It's not going to be so heavy that you're not going to be able to hold it up straight anymore. That's not what would happen. Now, if I got a bowling ball, or if I got something very heavy, I'm trying to think another circular object, maybe like a basketball or a soccer ball, a real soccer ball. Maybe if I throw it on now, you might notice that instead of your bed sheet being completely straight, it's now going to be a bit deformed. Those balls, if you look underneath your bed sheet, they might have their own little, circle, this little half circle showing where they are. So why is this kind of somewhat of a good analogy for how Einstein's viewpoint works? Well, Einstein's viewpoint is this. Given the fact that things cannot travel faster than light, you need to understand that there needs to be a way for you to get gravity to this other kind of being body. So, for example, there needs to be a way for the sun to have gravity on the Earth, but and there needs to be some kind of proper way of thinking about this, some proper mechanism, some proper way of getting the gravity there, but that still obeys the fact that gravity wouldn't be able to travel faster than light. So how do you kind of resolve this? So the way you resolve this is using this idea of having kind of heavy objects on this bed sheet. And you can think about it this way. When you put the coin into one of these kind of circular things, the coin starts circling around. It does so for 30 seconds. But you can think about it, well, what if you just put the coin in and then it just circles along the same path, just indefinitely. So that's kind of the idea of gravity. You have the sun is there, and then because the sun is so heavy compared to the earth just kind of rolls around it like a coin. And it just continues doing this forever and ever and ever. And the path that the earth follows is not exactly, whatever you've heard probably, traces out an ellipse. It's not exactly that. It's not perfectly any shape really, but it is some form of a kind of ellipse. It's some form of a not a perfect circle. It's kind of like elongated, and it just roams around. And the Earth is constantly jittering along. And so what's going on is that it's kind of this coin. When you flick the coin, you can see the coin. Like when it moves around, it kind of jitters around. It kind of teeters and totters. But the coin still follows on its path. It's still following on its path. It's still obeying. Going around that bowl. And that's exactly what the Earth does. So what the gravity is doing from the sun is that because the sun is such a heavy body, it distorts what is called space-time. And all this means is that essentially, in some very weird way, the universe, our solar system, kind of, you can think about it as sitting on this sheet of, this bed sheet. You can think about it as this sheet. And then as you place really heavy things on it, what it does is it kind of distorts it. It kind of just pushes it in. It creates these kind of, holes in this, universe, this space-time, as you might have heard. And then in doing so, that's what gravity is. Gravity is just, if I put that coin in that bowl, it's moving around it. And it does so stably. That is kind of what gravity is. So gravity is not this thing that essentially can go as far as it wants in the universe. And then it, by you moving around, dictates how far, dictates how strong it is, how not strong it is. And then in some weird way that you walking around your house is affecting a star, millions and millions of light years away. That obviously doesn't make any sense. Does it make more sense, though, that around you, kind of in your immediate environment, like, for example, the sun, its immediate environment is all of our planets, that it exerts that force on those planets, that it kind of, I want to use this word local, but immediate surroundings, that it forces those objects to kind of obey the fact that it's really heavy, and then it's caused this kind of bowl to form, where if you fall into that bowl, you're now going on a slightly different route. So think about it as like one of the big experimental confirmations of Einstein's idea of it, because again, it's not exactly a bed sheet, but it's a good analogy for what's going on. One of the big confirmations came from a guy named Arthur Eddington, and Arthur Eddington took a voyage to go visit an eclipse, a solar eclipse. Now this was around World War I, so it was a bit dangerous. I don't remember exactly where he went to go see this, but there were some issues with the authorities. I believe it was in Germany or something like this. He went to go see this ellipse. But anyway, eventually he got some data back. And what did he do? He took a photo of the solar eclipse. He took a photograph of it. You might ask, well, why would you want to take a photograph to measure, to understand, is Einstein right? Did Einstein get it right? Is this idea of these objects getting sucked into this kind of bowl that is created by these really heavy things, that somehow is gravity, that's somehow gravity, and somehow Newton got this wrong? So the way it was confirmed is, you have to think about it this way. Like, let's say you have a really big ball here, and you're on your bed sheet, and let's say some way you're able to put enough force on like a coin or something, or like some, I don't know, some object, some ball or something. So you have the larger, heavier object here, and it's caused this kind of, this kind of divot in your bed sheet. And what you're going to do is you're going to take this ball, and you're just going to essentially take it, not directly on where the ball is, but you want to take it a bit to the right. And if you just push this ball along, you'll notice that eventually you'll go into this divot, and then you'll come back out. If you just hold it straight, like don't let it go. But if you just kind of push this thing along, you'll notice that you'll go into it for a bit, and then you'll come out. So the idea here is that when you went into that little divot in the bedsheet, you have now been affected by gravity. That's because that's what gravity is. It's just this divot. It's the fact that it's curving. It's the fact that you're getting pushed into the sun. That's gravity. And then what Eddington did is essentially did what you do is you look at, based on Einstein's, I'll say equations, based on Einstein's predictions that you can get out, the numerical values that you can get out of what he wrote down in terms of the math. You look at, if I look at light coming around from the sun where the moon is blocking, if I look at the light around there, And if I do a very similar thing, I'm pushing this light beam, and I expect the light beam, when it gets close enough to the sun, is going to turn a bit. It's going to turn, it's going to warp. And I should be able to measure how far it warps based on how heavy the sun is, and the things I know about light. I should be able to measure how far this coin, or you can think about it any way you want, how deep into this thing I expect it to get curved in before it kind of shoots out. Um, you can kind of think about it as like shooting billiard balls. So, after you play a game of billiards, people generally like to use their hands and toss things. And what you can think about it is, let's say you just take a billiard ball and you just slowly push it. And then someone comes along and they just ever so slightly just tap it a little bit. They tap it, and then you tap it again, and then you tap it a little bit. Or you try to put some spin on your billiard ball. It's the same thing. You should be able to measure the effect that the sun has on this beam of light that was supposed to go straight. It's actually supposed to just go through and just shoot through. How far this beam of light gets pushed in by the sun, and you should be able to measure that. And that's exactly what happened. Eddington was able to measure for some light beams the angle at which it got kind of redirected. He was able to measure this, and that was the first big kind of confirmation of Einstein's prediction. And sorry, this video did go quite a bit longer, and I'll end it here. But my only recommendation would be, if you are interested in this idea of action at a distance, please go on the Wikipedia. I can link it in my description. It is very interesting and very philosophically relevant as to why Einstein came about. And again, I'm just going to continue on with how these two massive figures link up. In my next video, I'm probably going to start a new series and hopefully talk about some of my opinions on math education in Ontario, and talk a bit about higher mathematics and some concepts that I think are taught very poorly, and then hope I can clarify slightly what the issues I had growing up, understanding them, and then maybe helping you to see something a bit more artistic, a bit more creative, a bit more interesting about STEM, instead of viewing it as kind of a very mechanical, very cold, a very kind of boring kind of a thing. Because I similarly feel the same way about using the word science all the time. I think science doesn't really mean anything by itself, but there's a lot of very beautiful things that people have shown, that we as human beings have the ability to understand. And it's in that understanding that it's very beautiful. And so I'll leave you with that. And I'll hopefully be releasing a third episode of this soon. But hopefully probably my next video will be talking about math education. Thank you for watching. If you've gotten to this point, I would say this now: like, subscribe. Thank you very much. Talk to you next time.